G'day and welcome back to McGrathmatics, one of the YouTube channels of all time. Today I'm taking you through the normal distribution for my standard and advanced homies trying to get you exam ready for your HSC. I'm going to take you through the entire topic as quickly as I can, getting you all the important info and absolutely nothing else. So let's dive in. Let's talk about what a normal distribution, which is actually a hard word to say to me, is. So let's say I measured the height of 1,000 dudes. Don't ask why, just go with me on this, okay? We're going to graph their heights on a histogram like this. We're going to have a frequency on our y-axis, and the x-axis is going to be the heights. So in the middle, we're going to have the average heights, and then towards the upper end, we'll have our lanky blokes, and then down the lower end are our short kings. Now, what you're going to find, if you record the heights of 1,000 people, is that the average height in the middle is going to be the most frequent. That's what average means for most things. All right, it's the most likely thing to occur. Now, as you move further away from average height and you get taller and shorter, what you'll find is these heights are going to be less and less common. So going a little bit away from the mean is going to look like this. And then as you go further up each end, the frequencies are going to go lower and lower until we get this sort of shape, which we affectionately refer to as the bell curve, because it kind of looks like a bell. So when we're talking about a normal distribution, we are talking about a distribution of this shape, where the most common part is the middle, which is also our average. And as you get further and further away from the average, the frequency dips off rather quickly. Okay, so let's run through a quick example. So we have a normal distribution bell curve like this. In the middle, I've got X bar, which means the mean. And that's actually the same thing as the median and the mode. So mean, median, mode, all in the same place. Now, we're going to use this symbol today for standard deviation. This is a Greek letter called sigma, which when you teach teenagers is a very funny word. So hopefully you get a little giggle out of that. And for this example, we're going to say our mean is 75 and our standard deviation is 25. Now, what you're going to find in a normal distribution is if you go one step up and down from the mean, and when I'm talking steps, I'm talking this number here, which is standard deviation. So if I go up by 25 and down by 25, I get 50 and 100. Now, in a bell curve distribution like this, you're going to find between these two numbers is going to be most of your data. It's going to be 68% of the data set within this part here, because most of it is hanging around the average. Now, if we go up and down by two steps, so I add 25 again to each ends, so I'm going down to 25 and up to 125 now, what you're going to see between these two numbers is 95% of your data set. Okay, so these are the magic numbers for the normal distribution topic. And the last magic number is if I do 3 steps down and 3 steps up, so -3 and +3. Apologies if you can hear my dogs having absolute words with the neighbors in the background. They're very poorly trained. Anyway, so 3 down and 3 up is going to be almost the entire data set. You're going to be having 99.7% of your data set between these two numbers. Okay, so these are the 3 magic percentages we're working with for most questions in this topic. 68 between 1 up and 1 down. 95 is 2 up and 2 down, and 3 up and 3 down is 99.7%. Now, don't stress about remembering these percentages, because if you forget them, they are on the reference sheet. They give you a nice little bell curve here, and they have 68, 95, 99.7. All right, let's do a few examples of using these numbers and get you a little bit more comfortable. So here's our first one. Before we're going to do our first one, just a quick reminder of the properties of a normal distribution. Like I said, we have mean, median, mode smack bang in the middle, and we have a perfectly symmetric data set, 50% below the mean, 50% above the mean or median, as you would expect. This leads into a question from last year's or 2 years ago's HSC exam, and it was a band 5 because a lot of people struggled to pull 2 marks on this one. They gave you a picture of a histogram and it shows scores on a test. The question is asking you to provide 2 features of the graph that indicate that the data comes from a normal distribution. So what you want to say about this is about the shape and about the location of the mean, median, and mode. So we can see in the middle that our most common score, our mode, is also our median, and it's pretty safe to assume that because this is a symmetric data set, when you have a symmetric data set, the mean is also going to be in the middle. So we could easily say median equals mean equals mode to pick up a mark. We can talk about the fact that it is a symmetric distribution because the left and right hand sides match up, so that is a property of the normal distribution. And we could also say it is unimodal. It's got one peak, and that peak is in the middle where our mean and median are. Any of these 3 points would have got you 2 marks in the 2023 HSC exam. Let's do another one. We have an example. We have the ages of people at Comic-Con are normally distributed with a mean of 28 and a standard deviation of 9. What percentage of attendees are? We've got a bunch of questions. Okay, whenever I see a question like this talking about a normal distribution with a mean, standard deviation, and some percentages, First thing I do is sketch myself a quick little bell curve, and then I put some numbers on, and it's going to make the question 1,000 times easier. So in the middle, I'm going to put my mean, which is 28. And for this one, my step size, my standard deviation is 9. So I'm going to go up and down by multiples of 9. So I'm going to draw some lines. And here I'm going down by 9 to 19 and up by 9 to 37. Now I'm going to go up and down by 9 again. So 37 plus 9 is 46, and 19 minus 9 is 10. And then getting the third steps of 1 down here and 55 up here. So here are my numbers. Now I can answer the questions. First question is, what percentage of the attendees will be over 28? Now 28 is our mean, that's right in the middle. And like we said, our distribution is symmetric. So above the mean is going to be half the data set, which is 50%. Okay, for between 10 and 46, I can see my 10 is right here. This is 2 steps below, and 46 is up here, which is 2 steps above. And as we just mentioned, 2 down and 2 up is going to trap 95% of your data set. So 2 below and 2 above traps 95% of the scores. Okay, for 19 and 37, 19 is 1 step below the mean, and 37 is 1 step above the mean. So as we mentioned before, this section here traps 68% of our data set. Now for between 28 and 37, that's from the mean to 1 step up. Now we just said that 1 step down and 1 step up is 68%. So if I want to just go from the middle to 1 step up, all I've got to do is take that 68 and just divide it by 2 to get this strip here. Okay, and half of 68 is 34%, and that's going to be our percentage between the mean and 37, 34%. Okay, for younger than 19, down here, that's a little bit tricky. I want to go from 19 all the way down to the end of the rest of the data set. So for my mind, the easier way to figure that out is to see what percentage is above, because I know that from the mean up to the end is going to be 50%, 50% above the mean. And as I just explained, between the mean and 1 step below or 1 step above, just like in question C, this section here is going to be 34%. So I'm saying to myself, well, if up here is 50% and in here is 34%, if I add these two together, I get 84%. Okay, so if there's 84% above 19, I can just take 84% away from 100%, and that gets me 16% as my answer. Okay, so once again, there's 50% in this section, there's 34% in this section. So if I take those away from 100, it's going to leave me with the rest, which is 19 and below, which is only 16% of my data set. Okay, and for the last one, we have older than 55. 55 is 3 steps above my mean, which is just up here. And I want to find the percentage in this little tail up here. Okay, so my approach here is that I know from the magic numbers on the reference sheet that between 3 up and 3 down from the mean, as we said, is 99.7. That means the remainder that's left over in this tails is the remainder from 99.7 up to 100%. And so when you take 99.7% away from 100%, you're only left with 0.3%. So there's a very small amount in these two tails. But for this one, I want older than 55. I just want one of the tails. So I'll take that remaining 0.3% and I'll cut it in 2. And what I get is 0.15%. So there's 0.15% up in this tail and there's 0.15% down in this tail. So that's my answer for question F, 0.15%. Okay, let's do another one from an HSC paper from a fair few years ago. We have 10,000 newborn babies with normally distributed weights. They have a mean of 3.1 kilograms and a standard deviation of 0.35. We want to find how many newborn babies will be between 2.75 and 4.15. Okay, just like with my approach from the previous question, I'm going to get a better understanding of where these numbers are lying by drawing myself a bell curve. It doesn't have to be a beautiful work of art, it just can be a really quick sketch. Mine's going to be beautiful because it's digital, but yours will probably be crap. So we're going to put in the middle is going to be our mean of 3.1. So I'm going to put 3.1 just here. And I'm going to start adding my step sizes and taking away my step sizes of 0.35 until I've got my two numbers that I need, which is 2.75 and 4.15. Okay, fortunately, when I go one step down from 3.1 and I take away 0.35, that straight away gets me to 2.75. Okay, 3.1 take away 0.35 gets me 2.75. So this number is one step below the mean. Okay, now adding some numbers to get up to my 4.15. Taking my mean of 3.1, adding on 0.35 gets me to 3.45, so we're not there yet. I'll add on 0.35 again, which brings me up to 3.8, still not there. So adding it once more, 3.8 plus 0.35 gets me up to 4.15, and that's the second number that I need to answer this question. So now I've figured out that the babies I'm looking at are between -1 or 1 below the mean and up to +3. So I'm just going to figure out what percentages lie in these regions. So let's split this into two sections. Whenever I'm trying to find a percentage between two numbers and it's going through the middle, I always do left-hand side and right-hand side. It makes it easy for me, so I recommend you do it as well. Okay, so in this section here, as we've already mentioned, between the mean and one step below, because we know from one step below and one step above is 68%, this section in here is just going to be half of 68%, which is 34%. Nice and easy, right? Now to find from the middle, or the median, or the mean, up to +3, which is up here, I know from before that from 3 above and 3 below, that's going to trap 99.7% of my data set. There's the magic number. So if I just want from the middle up to +3, I just need to do half of 99.7% for this section here. And half of 99.7, would you believe, is 49.85. So there's my percent for the blue section on the right-hand side, and the left-hand side we have 34%. So combining these two percentages together and adding them, I end up with a total of 83.85%. So now to answer the question, our entire data set was of 10,000 babies, and so 83.85% of them are going to be between these two numbers. So I've just got to do 83.85% of 10,000, which is nice and easy. It just gets me 8,385, which is option D. Okay, so for this one, the 1 mark for the multiple choice was for D, 8385. Okay, now let's talk about the second part of this topic, which is all about the term z-scores. So we had this bell curve before with our magic numbers percentages, and we were talking about plussing and minusing our standard deviations. Another way of thinking about these numbers on my x-axis is to call them +1s and -1s. Okay, so these numbers here, where this number is basically how many standard deviations above or below I am, we call these z-scores. Okay, so a z-score is a measure of how many standard deviations above or below the middle you are, which is what that just says. There's a little formula you can use to for you to that. Sorry. All right. So as an example, to give you an idea what I'm talking about, we had a math test. The average mark was 55, and the standard deviation was 10. So let's think about Rory. Rory scored 65, and 65 is 10 above 55. So Rory is 1 standard deviation above the mean. That means Rory has a z-score of +1. Now Ava, not so lucky, she scored 35 on the test, and 35 is 2 lots of 10 below 55. So Ava is 2 standard deviations below the mean. So Ava has a z-score of -2. And our third customer is Zoe, who scored 80, and from 55 up to 80 is 25. And so she's done the standard deviation of 10 2.5 times. So a lot of the time, z-scores will be whole numbers, but they don't need to be. In this example, Ava's z-score was 2.5 because she is 2.5 standard deviations above the mean. Okay, so when they're nice numbers, you can kind of do them in your head like we did just here. When they're a bit more decimally and a little bit harder to see, we're going to use the z-score formula, which I'll show you now. So z-score formula, this is how we calculate them. We do the difference between the original score, x, which is also called the raw score, difference between that and the mean. This symbol here is another Greek letter called mu, which symbolizes the mean. It's another way of writing x bar. And we're dividing that by the step size, which is the standard deviation, aka sigma, aka hilarious word. So that is on the reference sheet if you forget it. It doesn't tell you what those letters mean, so you need to know that the z is obviously the z-score. X is the original raw score that we are trying to turn into a z-score. Mu is the symbol for the mean, and sigma is the standard deviation. All right, so you don't need to memorize what's in the blue box, but you do need to memorize what these symbols mean if you want to use this formula effectively. Okay, let's do some examples, and like I said, just there on the reference sheet. Doesn't tell you what it all means, but it is there in case you forget. Let's do a quick example of using this formula. This is from last year's HSC at the time of recording. We have P as marks in Year 10 assessments as shown, and all subjects were normally distributed, which means we can apply z-scores to these. We have her original mark on each test, we have the average mark in each test, and we have the standard deviation on each test. The question wants us to say which subject did she perform better in compared to the rest of Year 10. Okay, whenever a question is asking you to compare two scores in different data sets or compare different results on different tests, this is a question telling you to use your z-score formula. So we're going to get some good practice here by using this formula 4 times to turn all of Pia's raw marks into z-scores, so we can effectively compare them and say which one is the best and which one is the worst. So we're going to do 4 z-score calculations. Okay, first one is English. So in English, the raw mark, which is the X, is going to be 78. The mean is going to be 66, and the standard deviation on the bottom is going to be 6. So our calculation looks like this. 78, take away 66, divided by 6. That gets us an answer of +2. So in that test, PR was 2 standard deviations above the average. Now let's look at maths. In maths, the original score was 80 and the mean was 71. So we're doing 80 minus 71. Dividing that by the standard deviation of 10 gets us a result of 0.9. So Pia's maths is not as good as her English. Maybe she isn't subscribed to Mathematics yet, but she's only in year 10, so give her a chance to improve. All right, see what's going on in science. In science, we're doing 77, take away 70, because we're doing raw score, take away mean, dividing by the standard deviation of 15. So because this standard deviation is much larger than 6, it means that the science data set is much more spread out. So don't forget, standard deviation is just a measure of spread. Okay, this calculation gets us an answer of 0.46 repeater. So far, science is the worst result, but we should probably check history before we conclude. History's calculation is 85 take away 72, being divided by 9, which gives us a z-score of 1.4 repeater. So from our results, it seems that compared to the rest of her cohort, Pia did the best in English and she did the worst in science. And we're trying to say which one did she do the best in. And the answer for that one is the first z-score, which is English. So it is a bit of a stitch up because you got to do 4 things for 1 mark, but it's a quick, simple little formula. And once you've used it a few times, you'll be very comfortable. Okay, let's do another one from the 2019 HSC. This one's a band fiber, so it's pretty tricky. For 2 marks, we have in a particular country, birth weights of babies again. I don't know why NASA is obsessed with the weights of babies. Anyway, normally distributed with a mean of 3,000 grams. It is known that 95% of these babies are between 1,600 and 4,400. Okay, 95% is a percentage we've seen before. That's going to be useful. One of these babies has a birth weight of 3,497 grams. What is the z-score of this child? Okay, so if we want to find the z-score of this number using the formula that we were using on the previous slide, we need to know the original score, which we know. We need to know the mean, which we know, but we also need to know the standard deviation, which we don't know. So we have to figure out the standard deviation in this data set so we can turn this number into a z-score. So let's do a little bell curve. In the middle, we have 3,000, and it says that 1,600 and 4,400 is trapping 95% of our data set. Luckily, we know our stuff, and we know that 95% is corresponding to +2 and -2, okay? Between 2 up and 2 down is 95% of the data set. So I can put the 1,600 down here, and I can put the 4,400 up here. Okay, so what I'm seeing here is that from the mean to 2 steps up, this gap here is 1,400. So if there's 2 steps happening here, that's giving me a difference of 1,400 grams. I can just divide that by 2 and I'll be able to figure out what my standard deviation is so I can then answer the question. Excuse me. Okay, so 1,400 cut in half gets me 700. So that tells me that for this data set, the standard deviation is 700. Now I've got that, I can rip into my z-score formula once again. Okay, so X is my original score, which is the baby's weight of 3,497. Mu for mean is going to be 3,000, and we just figured out that our sigma is 700. So let's sub that all in and see what we get. We're trying to find the z-score, so we just got to answer this question here, chuck it into the calculator, and we get an answer of 0.71 for this baby's weight as a z-score for 2 marks in the 2019 Band 5 HSC question. Okay, how many more are we doing? 1 more, I think. Okay, this question is a really tricky Band 5 from 2023. These questions are occurring in pretty much every year's exam, so it is important that you're comfortable with questions that look like this. When your z-scores are going to be whole numbers, you can use the numbers from the reference sheet, which are 68, 95, 99.7. When your z-scores are decimals, like in this table here, and they're wanting you to find some percentages between those z-scores, they're going to give you those percentages in a table. Okay, so when z-scores are whole numbers, you can use the numbers on the reference sheet. When the z-scores are decimals, they will give you a table and probably a picture like this as well. This question is worth 4 marks, and it's got a lot of reading, so let's just rip into it. We have a random variable, normally distributed, mean of 0, standard deviation of 1, which is just a z-score basically. The table gives the probability that this random variable lies below z for some positive values of z. Now, that is a very confusing sentence, or couple of sentences. All it is saying here is that if you want to find the percentage of the data set up to a specific z-score, look at the table. Like for example, if this z-score right here was at 1.3, so that was 1.3, this shaded area would be 0.9032, which is equivalent to 90.32%. Okay? So all this question is trying to confuse you with is that the percentage up to a certain z-score is given in the table, okay? Now we know that, we can try and actually answer the question. So the actual question is, the weights of adult male koalas form a normal distribution with a mean of 10.4 and a standard deviation of 1.15. In a group of 400 adult male koalas, how many would be expected to weigh more than 11.93? Okay, so we want to use this table and this picture to figure out what percentage are going to be above our weight of, are going to be above our weights of 11.93. Once we figure out that percentage, we can apply it to the total data set, which is 400, and hopefully get an answer. Now, as we can see, this table is all talking about z-scores. So the first key to this question is, hey, if I want to use this table and use this picture as well, I'm going to need to figure out what the z-score of 11.93 is. So that's where we're going to start. Here is our z-score formula once again. X is our original score, which is the koala's weight of 11.93. We have the mean in the question, which is 10.4, and we also have the standard deviation, which is 1.15. So I'm going to sub those values into this formula, our weight, mean weight, standard deviation. This gets me a value of about 1.33, which is good because 1.33 is one of the values in the table, so it makes me feel like I'm probably doing the question right. Now, the table says that 1.33 corresponds to 0.9082. What that means to me is that if this z-score right here was 1.33, there would be 90.82%, okay, just timesing that by 100, 90.82% of the data set would be below a z-score of 1.33. Now that's really useful because if there's 90.82% down here, this question is asking us to find how many are going to be more than 11.93. So I want to find the percentage that's above this z-score of 1.33. So that's nice and easy. I'll just take that 90.82% away from 100%, giving me a remaining 9.18% up here. And that's the hard part of the question done, because now the question already told me that the entire data set is 400 koalas. I'm trying to find 9.18% that are up here. So I'm just going to do 9.18% times by 400. And that gives me an answer of 36.72. Now, it doesn't really make sense to say 36.72 koalas. So probably a better answer would be to round it up to 37. Although I checked the markers feedback from that year, and they also accepted 36, and they also accepted 36.72. So out of the 4 marks in this question, none of them were for rounding. So if you get to this point and leave your answer like that, it is going to be all okay. But that is how you do this 4% of the 2023 HSC exam. And that's my whole run through of the normal distribution topic for you. Hope that helps and help you get a little bit more confident in this topic leading up to your HSC. If you made it to the end of that, thanks so much for watching, and I wish you all the best for your HSC. If you have a friend who you think is going to fail their HSC, maybe flick them this video and try and save their ATAR, but if not, no worries. All right, thanks again, and I'll catch you in a new revision video pretty soon. And yeah, like I said, good luck for your HSC and all the best. Bye.